What if I told you that the ancient Romans developed a technology so revolutionary that it could feed an entire city of over 1 million people? Today, we're diving deep into one of Rome's most underrated innovations, the Roman mill system. From simple hand-operated querns to massive water-powered complexes that produce tons of flour daily, Roman mills were the backbone of an empire that stretched across 3 continents. To understand why Roman mills were so important, we need to grasp the sheer scale of Rome's grain consumption. The city of Rome alone had over 1 million inhabitants at its peak, and wheat was their primary staple food. Every single day, these people needed bread to survive. Before mechanical mills, grain processing was backbreaking work done by hand. Women would spend hours bent over grinding stones, crushing grain kernel by kernel. Archaeological evidence from sites like Tel Abu Hurira shows that this manual labor causes severe skeletal deformities, spinal problems, knee arthritis, and foot deformation from the constant grinding motion. The Romans inherited simple grinding tools called querns from earlier civilizations. These consisted of 2 stones rubbing against each other, with grain crushed between them. But as Rome grew from a small city-state to a vast empire, these primitive tools simply couldn't keep up with demand. The Romans needed an industrial revolution, and they got one. Roman mill technology evolved in 3 distinct phases, each more sophisticated than the last. The first breakthrough came around the 3rd century BCE with the development of the rotary quern. Unlike earlier back-and-forth grinding motions, this innovation used circular rotation, making the process more efficient and less physically demanding. These early rotary querns were still operated by hand, but they represented a crucial conceptual leap. The Romans had discovered that continuous rotational motion was far more efficient than reciprocating movement. But the real game changer was the donkey mill, or what archaeologists call the hourglass mill. These iconic machines, which you can still see preserved at Pompeii today, consisted of 2 parts: a bell-shaped lower stone called a meta, and an hourglass-shaped upper stone called a catalyst. The design was ingenious. Grain would be poured into the top of the catalyst, and as it rotated around the stationary meta, the grain would be crushed and gradually work its way down through the narrowing gap between the stones. By the time it emerged at the bottom, it had been transformed into flour of remarkably consistent quality. The catalyst would be rotated around the meta by donkeys or sometimes by enslaved people, crushing grain in the hollow space between the stones. These mills were made from volcanic basalt, chosen for its perfect balance of hardness and porosity, hard enough to crush grain efficiently, but porous enough to prevent overheating from friction. The Romans were so particular about their millstones that they imported the best basalt from specific quarries, particularly from the volcanic regions around Mount Vesuvius and the German Rhineland. The precision required in crafting these stones was extraordinary. Master stonemasons would spend weeks shaping each stone to exact specifications. The surfaces weren't smooth. They were covered in carefully carved grooves called furrows that helped move the grain through the mill and prevented the flour from becoming too compacted. What made these mills revolutionary was their capacity and consistency. A single donkey mill could process far more grain in a day than dozens of people working with hand querns, and the flour quality was remarkably uniform. But Romans didn't stop there. The introduction of water power completely transformed milling technology, and this is where things get really fascinating. The Roman architect Vitruvius documented water-powered mills as early as the 1st century BCE, and archaeological evidence shows these sophisticated machines spreading across the empire like wildfire. The basic principle was elegant in its simplicity. Flowing water would turn a wheel, which through a series of gears would rotate the millstone. But the engineering challenges were enormous. Romans had to figure out how to transfer the horizontal motion of a water wheel to the vertical motion needed to turn millstones. Their solution was the gear system. They developed sophisticated wooden gear trains that, could change both the direction and speed of rotation. The most spectacular example is the Barbigel Mill complex in southern France, which operated from the 2nd to the 3rd century CE. This wasn't just a single mill. It was an industrial complex featuring 16 water wheels arranged in 2 parallel rows down a hillside. Water from a Roman aqueduct powered the entire system in a carefully engineered cascade. Picture this. Water would flow down from the aqueduct, hit the first wheel, power its millstone, then continue to the second wheel, and so on down the hill. Each wheel was precisely calculated to extract maximum energy from the flowing water while leaving enough to power the wheels below. The Romans had essentially created the world's first industrial assembly line. The capacity of Barbigel was staggering. Conservative estimates suggest it could produce 4.5 tons of flour per day, though some researchers believe it could have reached 25 tons daily. That's enough flour to feed between 10,000 and 80,000 people every single day from just one mill complex. To put this in perspective, that's more flour than many modern commercial mills produce. These water mills represented a quantum leap in productivity. While animal-powered mills needed constant supervision, feeding, and care for the animals, water mills could operate continuously as long as water flowed. They were the ancient world's first automated factories, running day and night with minimal human intervention. But the Romans didn't just build mills wherever there was water. They engineered entire landscapes to optimize mill performance. In some locations, they built elaborate dam systems to create artificial ponds, ensuring steady water flow even during dry seasons. In mountainous regions, they carved channels through solid rock to redirect streams to their mills. The engineering behind Roman mills was surprisingly sophisticated, and the more archaeologists study these machines, the more impressed they become. Romans developed both horizontal and vertical water wheels, each optimized for different conditions. Horizontal wheels, called Norse wheels, worked better in areas with fast-flowing streams and required less complex gearing. Vertical wheels were more efficient for locations with steady but slower water flow and could generate more power, but needed sophisticated gear systems. But here's where it gets really interesting. Romans didn't just build mills, they built integrated milling systems. The mills weren't just about grinding grain either. Roman engineers adapted the same technology for crushing ore in mines, sawing marble and wood for construction, powering trip hammers for metalworking, and even powering bellows for iron furnaces. At the Rio Tinto mines in Spain, archaeologists have found evidence of water-powered ore-crushing mills that could process tons of copper and silver ore daily. This versatility shows how Romans thought systematically about mechanical power. They didn't just invent a grain mill. They invented a comprehensive power system that could be adapted for any rotational task. The millstones themselves were precision instruments that would impress modern engineers. The gap between the stones had to be perfectly calibrated. We're talking about tolerances measured in millimeters. Too wide and the grain wouldn't be ground fine enough. Too narrow and the stones would jam or overheat from friction. Roman millers developed sophisticated techniques for dressing or resharpening the stone surfaces using special picks and chisels to maintain optimal performance. The furrow patterns carved into the stones weren't random either. Different patterns were used for different types of grain. Wheat required different furrows than barley or rye. These patterns were closely guarded trade secrets passed down through generations of miller families. Even the mill buildings were engineered marvels. At Ostia, Rome's port city, archaeologists have found integrated mill-bakery complexes that would make modern industrial engineers jealous. These facilities had specialized rooms for different stages of bread production, grain storage areas with raised floors to prevent moisture damage, milling rooms with carefully designed ventilation to remove flour dust, sifting rooms where different grades of flour were separated, and kneading rooms with built-in stone basins. The Romans even solved the problem of flour dust explosions. a hazard that still plagues modern mills. They designed their milling rooms with specific airflow patterns and used water sprays to control dust levels. This wasn't accidental. Roman engineers clearly understood the explosive nature of airborne flour particles. One of the most ingenious innovations was the Roman bolting system, an early form of flour sifting. They used cloths of different weaves to separate flour into various grades of fineness. The finest flour went to make bread for the wealthy, while coarser flour was used for ordinary citizens' bread. This wasn't just about quality control. It was about maximizing profit from every grain of wheat. Roman mills didn't just change technology. They transformed society in ways that still echo today. The efficiency of mechanical milling allowed Rome to support unprecedented urban populations. Without these mills, cities like Rome, Alexandria, and Antioch simply couldn't have existed. But the social implications went far deeper than just feeding people. The mill system created entirely new economic structures. Professional millers became wealthy and influential citizens, forming powerful guilds that controlled grain processing throughout the empire. The Collegium Pistorum, the Roman Bakers' Guild, was so important that emperors personally appointed its leadership. These weren't just craftsmen. They were essential infrastructure operators whose work kept the empire stable. But this technological revolution came at a human cost, and recent archaeological discoveries are revealing the darker side of this story. In 2023, archaeologists uncovered what they recalling a bakery prison at Pompeii, a facility where enslaved people and donkeys were confined together to operate mills around the clock. The evidence is deeply disturbing. Barred windows at human height, but open spaces higher up for ventilation. No external views to prevent escape attempts, and spaces designed to house both humans and animals in the same confined area. The mill operators lived, worked, and slept in the same rooms as the donkeys that powered the mills. Iconographic evidence from the tomb of Eurysaces in Rome, a wealthy baker who made his fortune from mill operations, shows the reality of this system. The relief carvings depict both enslaved people and donkeys working together at the mills, with human workers not only helping push the massive millstones, but also managing the animals and monitoring the grain processing quality. What makes this particularly tragic is that these weren't unskilled laborers. Operating a mill required significant expertise, knowing how to adjust the stone gap for different grains, understanding when stones needed maintenance, managing the complex process of turning wheat into flour of consistent quality. These were skilled workers trapped in a system that treated them as barely more than the animals they worked alongside. The scale of this exploitation was enormous. Rome alone had hundreds of mills, each requiring multiple operators working in shifts to meet the city's massive demand for bread. Scholars estimate that thousands of enslaved people were trapped in this milling system throughout the empire. But the story isn't entirely dark. The efficiency of Roman mills also created opportunities. Some enslaved millers could eventually buy their freedom and establish their own bakeries. The wealth generated by efficient milling helped fund the Roman system of free bread distribution, the famous bread and circuses that kept urban populations satisfied. One of the most remarkable aspects of Roman mill technology was how it adapted to local conditions across the vast empire. In Britain, Romans built tide mills that used the rising and falling of ocean tides to power millstones, a technology so advanced that similar mills continued operating into the 20th century. Archaeological evidence from sites like Elling Mill shows Romans harnessing tidal power as early as the 2nd century CE. In the dry regions of North Africa and the Middle East, where water was scarce, Romans perfected wind-powered mills. These weren't the familiar European windmills with their horizontal rotating blades, but vertical axis mills with sails that caught wind from any direction. Remains of these mills have been found in locations from Tunisia to Syria, showing how Roman engineers adapted their basic milling principles to work in completely different environments. Perhaps most impressively, in mountainous regions like the Alps and the Pyrenees. Romans built mill systems that operated year-round despite freezing temperatures. They developed techniques for preventing water from freezing in the mill races, including underground channels and even primitive heating systems that used waste heat from the milling process to keep the water flowing. The standardization of Roman mill technology across the empire was remarkable. A miller trained in Gaul could operate a mill in Egypt or Britain because the basic principles and measurements were consistent. This standardization wasn't accidental. It was part of Rome's broader strategy of creating unified systems across diverse territories. The impact of Roman mill technology extended far beyond the fall of the empire, and in many ways, we're still benefiting from their innovations today. Medieval European mills were direct descendants of Roman designs, and many Roman engineering principles remained in use well into the modern era. But the organizational lessons were equally important, and perhaps even more influential than the technology itself. Romans developed sophisticated supply chains to bring grain from Egypt and North Africa to mills in Rome, then distribute flour to bakeries throughout the city. This logistical system was as impressive as the mills themselves and became the model for all subsequent large-scale food distribution systems. The Roman approach to quality control also established standards that persist today. They developed systematic methods for testing flour quality, grading different types of flour for specific uses, and ensuring consistent products across their vast network of mills. Modern flour grading systems can trace their origins directly back to Roman practices. Perhaps most importantly, Roman mills demonstrated the transformative power of mechanical advantage and systematic thinking. They showed how engineering could solve social problems on a massive scale, feeding populations that would have been impossible to sustain with earlier technology. This concept of using technology to solve societal challenges became a cornerstone of Western civilization. The Romans also pioneered the concept of industrial specialization. Rather than every household grinding its own grain, they created specialized facilities operated by trained professionals. This efficiency model became the foundation for all subsequent industrial development, from medieval guilds to modern manufacturing. Even today, when you buy flour at a grocery store, you're participating in a system that the Romans essentially invented: centralized processing, quality standardization, and efficient distribution networks. The story of Roman mills shows us that ancient people were far more technologically sophisticated than we often imagine. These were primitive societies stumbling toward progress. They were innovative engineers, solving complex problems with elegant solutions. What other ancient technologies do you think we underestimate?